Greetings, physical science classes. You guys have just gotten into class. The day, I guess, would be Friday, depending on when I show this. But you all just left for lunch. We just started learning about forces. And then as we get into the unit, we know that bell ringer is a great learning experience. So what we'll be doing to start here is going over bell ringer 1. You should have got that yesterday. If you need extra copies, they're either in the basket or the sub has them. But you should have given that your best effort for a few minutes, and now we're going to go through it together. So get forces bell ringer 1 out. This is the one that has 2 sheep on it to begin with. So as we dive in and look, everyone, at bell ringer 1, we mainly introduce the idea of forces and what they are and how we measure them. Number 1 says a big right hook punch, maybe from one co-teacher to another, if you know what I'm saying. But that could be measured as a force of 500 what? So we can't say meters, we can't say meters per second. We need to make sure we're paying attention to that again, but we learned yesterday that forces, everyone, are measured in newtons. Okay, so when we really zoom into this first one here, that would be newtons. We've been abbreviating that with just a capital N. Okay, but then we'll dive a little bit more into what a newton formally is as our unit picks up. Okay, but otherwise that's just kind of a knowledge question. Number 2, we're talking about Spike and Jimmy, 2 bighorn sheep, and it says the one on the right can apply a force of 345 newtons. Okay, that pushing the other way. The one on the left, Jimmy, has been getting stronger and can also apply a force of 345 newtons. So when we're back next week, we'll show a video of this, but their skulls are very, very special, and it sounds like a gunshot goes off, but this is how they fight for alpha malehood. So hopefully you really saw those numbers and you went, wait a minute, Spike can push with 345, Jimmy can push with 345. Hopefully we learned yesterday that if those two things are in opposite directions, they cancel out. So as far as describing what will happen, mine's probably a little bit wordy, but the forces are equal, but since they're in opposite directions, they will cancel each other out, and this is an example of forces being balanced. Okay, that's a big deal because that means neither sheep is really going to go anywhere because they'll cancel each other out. If you take 345 minus 345, the overall net force in this will be 0. Neither sheep is going to win, and in nature they have other ways of settling this, but when they hit each other, it's not going to go one way or the other because those two forces being balanced mean it will not accelerate. And what they'll do then is kind of just hit each other and it won't move one way or another because the forces are balanced. So make sure we're really thinking about this. If an object is sitting at rest, forces are balanced. If a car is moving at a constant speed and not speeding up or slowing down, the forces are balanced. On the flip side, if something is speeding up as it falls or slowing down to the stop sign, if it's accelerating, there has to be a force winning. So that's what we really want to keep thinking about, okay? The sub can pause it whenever they need to, otherwise let's keep going here. The bottom one, Smirch, this problem's so easy. Well, they're going to get tougher, but this sets up our habit. So we have a car, his engine is applying a force, the green force forward of 10 newtons. He deploys a parachute, that would be a force of 7 newtons, so that would be slowing him down there. With that being said, if we go think about it, we know that 10 minus 7, there is going to be a net force. The earlier one was 345 and 345. This one is 10 and 7, and if that's a tug of war, we know the green force is going to win. So if we take 10 minus 7, the net force in this case would be 3 newtons. And remember, we can't just say 3 newtons. We have to say 3 newtons with the direction. So in this case, the car is going to have a bigger force to the right. So these clearly aren't the same. What the car is going to end up doing then is having a net force to the right, so it's going to accelerate to the right. But this is a great example of forces being unbalanced. They are clearly not the same, and what that means, since they're unbalanced, is it's not just going to move to the right, it's going to speed up and accelerate to the right. Just moving to the right, it might have already been doing that. What we want to understand is that since the forces are unequal, that one's going to keep winning and winning and winning, and then it'll keep speeding up and speeding up, okay? Number 5 will get us thinking, if we were told the car was really heavy, how would that change it? We'll learn a little bit later today and then Monday that Newton's second law is where we talk about forces and mass and acceleration. So if the force is going to be the same thing, but now this mass is way higher, so if the mass goes up, if M goes up, what does A have to do? It has to go down. This would just be like if you pushed a chair with me in it and Mr. Weber's in it. I would clearly go way faster. If you push Mr. Weber's chair, he has more mass than me. No, that's not a fat joke, Mr. Weber's. But if this mass is higher, they're not going to go as fast. So in this case, everyone, if the car would be heavier, it's not going to accelerate as much. So it would either wouldn't slow down as fast or it would get going a lot slower as it accelerates, okay? That takes care of that. Now, on the back side, everyone, we learned yesterday about free body diagrams. These are those drawings where we're going to look at what forces are acting on it, and it's really going to help us set a lot of those up. So, key words, we're looking at constant or accelerating, slowing down, at rest. Number 1, everyone, says Mr. Weber's pedals his bike at a constant 14 miles an hour on a windy day. Okay, so the bike is underlined, so that's our free body diagram is our bike, and we know as Mr. Weber's pedals, his push on his pedals is going to make him go forward. Now, if you just left the diagram like this, it would show to me that he must be really speeding up, but it says he's moving at a constant speed. So there has to be a force the other direction, because constant speed means they're balanced. So what force would that be, everyone? If he's riding to the right, you could say a couple different things here, but what we said it is friction. Okay, friction is always opposite motion. So if he's riding his bike to the right, friction would be to the left. You could have also put the force of the wind or air here, but that really is a type of friction. It's going to slow things down. This is a thing too where we want to show those tick marks. I didn't know how to do that on my computer, but showing that they're equal. If you don't want to add the tick marks, that's fine, as long as you say or show, hey, these two forces are perfectly balanced, which means it's not going to accelerate. Its acceleration would be 0 because the net force is 0. And that makes a lot of sense now, because if our acceleration is 0 and we're going 14 miles an hour, what are we going to keep doing? Going 14 miles an hour. So as long as he's pedaling, he's going to keep moving that fast. If he stops pedaling, this arrow would get less, and that would mean he'd slow down. If he wants to go faster, he has to pedal harder than friction and the wind. Okay, so keywords though, constant means it's balanced. Number 7, everyone, the key giveaway is that it's thrown up into the air. Okay, so I got a tennis ball and I throw it up in the air. So I'm not touching it, but it's officially going. What do we know that tennis ball does? Well, when it first goes out of our hand, it starts out fast and then it slows, and then eventually it kind of even stops. So since it's slowing down, that would be negative acceleration or decelerating, but that tells us the forces can't be balanced, because otherwise the ball would just keep on going, which is actually what it does in outer space. Okay, so we got to know it's unbalanced. When we go draw, what do we always have to start? We always have the force of gravity. We know that that's going to be pulling the tennis ball down. Now, a lot of kids really want to go put an arrow up, and what they write is the force of the hand, but if let me move my camera, if I was throwing a tennis ball right now and it's going up, I'm not touching it anymore. So you can't put an arrow up right there because I'm not touching the tennis ball, right? Right now, no force, there's a force. As soon as you let go of the ball, your hand isn't applying a force anymore. What that really is called inertia. That means if the ball was going up, it's going to keep going up. But it won't in this case forever, because the unbalanced force of gravity is going to pull down on it. What we'll learn this is called, everyone, you should make this note, but it's going to be unbalanced, and this is called free fall. If gravity is the only force acting on an object, we call it free fall. It's a great song by Tom Petty. It's also a huge part of our parachute lab and stuff that we'll do. So that takes care of our tennis ball problem. But make sure, if you had a force up, cross it out, because you're not touching it anymore, so you're not applying a force. Number 8 is talking about Simi pulling her little wagon. It says, oh, I just realized I did not know, did I mess this up? No, I didn't. So Simi pulls with the force of 70 newtons to the left. So all I've done is say, hey, there's that force. I probably should have wrote the word pull right there, but we gave a value in this problem, so we should know that one's 70 newtons, and then it says friction is half of that. We know if Simi's pulling her wagon to the left, oops, it's opposite in the camera. If Simi's pulling the wagon to the left, friction would be opposite and to the right, and it says half of that. So if you take 70 divided by 2, that would mean her force of friction is 35. Now just looking at this, balanced or unbalanced, turn and tell your neighbor. Very good. So we can clearly see the one on the left is going to win. That would mean we have a net force to the left, which means it's unbalanced. And if there's a net force that's bigger to the left, that means it's going to accelerate and speed up. And in this case, Simi's going to be hauling down the street because the bigger force is winning. This is, again, it all comes down to the tug of war. Who's winning the tug of war? 70 minus 35 would mean this way is winning by 35 newtons, and that means she's going to speed up. Last one on here. We have Augie. He's the first corgi up on the poster there, but he's sitting on the patio watching for rabbits. Okay, so there's our little box. We don't need to draw a corgi, but we're on planet Earth. What force do we always know there is? The force of gravity. Now, if you just stopped right there and that's it, Augie would be falling. If he's just sitting there on the patio, is he falling? That answer is no. So there has to be a force upward, right? We have to know he's at rest. We have to know it's balanced. These two forces have to be equal. So again, you could make your little tick marks here to show they're equal. But why isn't Augie falling? This is like the snow globe one yesterday. That, if you think about it, Augie's not falling because the ground is pushing back up on him. And again, what will those two things do? They'll cancel out and he'll stay at rest. An object at rest will stay at rest. So these are balance forces. And again, I should have little tick marks. You could write the net force equals 0. I mean, if gravity's 500 newtons, the ground is pushing back up with 500 newtons. And 500 minus 500 would be 0. So this is going to show us they're balanced. He's not going to accelerate and he'll stay at rest there. Okay, so it's all about looking at those words and just getting good at knowing those forces, okay? Otherwise, the last one just says which of the examples are balanced. This would mean which ones are sitting still or moving at a constant speed. So our answers here would be Weeb's on his bike because he's pedaling as hard as friction is and it's just going to keep going at a constant speed. The tennis ball is unbalanced because it's slowing down. Simi's wagon is unbalanced because she's pulling harder. But Augie would be balanced. He's not accelerating, he's not speeding up, he's not slowing down, he's completely at rest, okay? So make sure we turn that in a minute here, but for the rest of class now, you guys will all get your blue assignments from yesterday, but the first assignment is all about net forces. So you're gonna do the whole front side right now, but pay attention to the key words when you get your blue sheet out. A mug is sitting at rest. A motorcycle speeds up. A dad pushes a stroller at a constant speed. Really think about those, and then you'll kind of go through with some numbers down here. Mrs. Pleskotch or whoever the sub is has a key. Why don't you do like 1 through 4 and then check the key, and then do 5 through 9 on the front and check the key. What you'll do then, everyone, once you've done that and checked every now and then, is you'll go to your school emails. I sent you 2 very short videos about Newton's second law, which is now going to make this mathematical. After those, you'll be able to finish and work on the back of assignment 1. And then with about 15 minutes left, the sub will hand out the parachute lab. That's where we'll really start looking at gravity and these forces next week. But you can start to do some research on your parachutes with your Chromebooks. We appreciate your guys' effort. Please stay engaged and focused and do your best. Otherwise, be productive, and we'll continue learning about Newton's laws on Monday.